Welcome. Welcome to the Stream Processing Meetup, our first meetup for 2019. We plan to have a meetup every quarter and hopefully you'll see a lot more interesting talks. We have a packed schedule. We have 3 talks as usual. We'll start with a Samza talk. We have Pratik from LinkedIn. We'll talk about the work that we have done in Samza 1.0. We'll talk about the future plans for Samza. We'll follow it up with the talk on Kafka. At LinkedIn, we built a product called Brooklyn Mirror Maker to replace Kafka Mirror Maker. And Shunping from LinkedIn is going to talk about it. We'll have a short break of 5 minutes, and then we'll have a guest speaker, Ritin. Ritin joins us from Facebook stream processing team, and Ritin will talk about Puma. Before we get started, a few quick FAQs. One of the most common FAQs I get from my team, do we have ice creams? Today we have ice creams. So we got that sorted out. The second most common question, do we record the sessions? Who am I? I always forget. Okay, I'm Samarth. I lead the stream processing and data pipelines team at LinkedIn. And I will introduce those guys. Yeah. So do we record the sessions? The answer is yes, we do record the sessions. All the sessions are in a playlist in YouTube. If you look for stream processing meetup on Google or go to our meetup site, you have a link for all our previous sessions. The other common question is, do we stream the sessions? Yes, we live stream all the sessions, but typically we post the link only a couple of hours before the meetup starts. If you scroll down the meetup invite, you will see a link something like this. This is not a link from today, but this is typically something you see at the end of the session, end of the meetup. The last thing people typically ask is, I want to present, who should I talk to? The best option is to post a message on the meetup site. There is a way to contact the organizers. We typically get a lot of requests there. We are not real time in responding, just not like our systems, but we try to respond every week at least. So post a message, we'll try to get back to you. The other option is talk to one of us. I'm Samarth and we have Nacho. Do you mind standing up? Nacho, who manages the Kafka team here. We have Clark. Clark is a SRE manager for stream processing. We have Christo. Christo is our program manager for streams infrastructure. So talk to any one of us today if you have a talk on Kafka or Samza or related stream technologies. One short announcement. We recently made around 6 videos on stream processing basics and Samza tutorials, right? So this is something that is also there on YouTube. If you are new to stream processing and want to get started, would recommend this. It is accessible through our site. You go to our site, you'll see a big bold red link which says Samza tutorials or stream processing tutorials. We're about to start. I want to welcome Pratik. Pratik has been in LinkedIn for over 4 years. He's a Samza PMC member. He's a tech lead of Samza. And he's going to talk about Samza 1.0. Samza 1.0, as I believe, is one of the biggest release since we went open source in 2014, right? And Pratik is going to talk about all the capabilities that we added in the last few years. And he'll also talk about our plans for Samza 1.0 in the future.
Can everyone hear me? Okay. Thank you for coming, everyone. Welcome to the Streams Meetup. I'm Pratik. As Sam mentioned, Samza recently reached a major milestone with the 1.0 release. And it's been a while since we talked about Apache Samza in this forum. So I want to give you a tour of what we've been working on in 1.0 and where we are going from here. So a quick show of hands, how many of you guys are already familiar with Samza? Or have heard of it, used it, been to one of our meetups before? Cool. I see some devs aren't sure. But with the stuff we've done in 1.0, it's not surprising. There's a lot of new stuff here. Cool. So for some background, like Sam just mentioned, Samza is a pretty old open source project by the standards of open source projects. It's been a top level Apache project since 2014. So it's been a good 5 years, and now we've finally decided to release the 1.0 version of Samza. And Samza is used at many major internet companies. We use it extensively at LinkedIn. It's been used at Slack, MetaMarkets, Intuit, TripAdvisor, etc. And even within LinkedIn, there are thousands of active jobs running in production at any given moment, thousands of Samza jobs. So here's a very zoomed out 10,000 feet picture of the nearline processing architecture or stream processing architecture at LinkedIn. So at the top, we have the services tier where all of our user requests, etc., go in. And then the data flows in LinkedIn through Kafka and primary data stores like Espresso, which is our internal data store, Oracle, MySQL, Ambry, which is our blob store, etc. And then change captured by Brooklyn. And then through Kafka and Brooklyn, it's consumed by Samza for near real-time processing, and then it's written back to these data stores and to the services directly. So you can think of if Kafka is the data pipeline backbone of LinkedIn, Samza is the stream processing framework at LinkedIn. And here's some numbers about the scale at which Samza runs at LinkedIn. So like I mentioned, there are about 3,000 jobs, Samza applications at any given time running in our production clusters. We process close to 1 trillion messages per day from Kafka and Brooklyn and other streaming sources. Across our clusters, we have over 3,000 machines with 99.99% availability. Right. At this point, I typically have a slide about who's using Samza, but these days the list is pretty long. That's basically everyone at LinkedIn. That's a whole topic for several talks by itself. But in general, it's used for many use cases. Some primary ones are notifications, trust and safety, like spam detection, bot detection, feed news, ad relevance, content classification, what's spam, is this a spam picture, is this just a viral picture, is it something useful? Search index updates, call graph computations, Kafka audit itself. There's a variety of use cases. And I'm sure we've talked about many of those in this forum. So back to the topic of the talk, let's talk about what's new in Samza, right? Our goal over the last year or so has been to enhance your developer experience and productivity. And all the work we've done broadly falls into these areas, right? We've worked on faster onboarding, which is to make it faster and simpler for you to develop new Samza applications. We've worked on a bunch of different APIs, which make it easy for you to express what you want to do at the right level of abstraction, depending on whatever you want to do. We've done a bunch of work to make it easy to develop your Samza applications. Part of it is offering the right kind of APIs, right abstractions for you to achieve your goals, and also to improve the tooling to get your stuff done faster. And then we've been focusing on better operability for Samza jobs. Like I mentioned, we run a huge Samza cluster at LinkedIn, so cost effectiveness and ease of operating this cluster is important to us, ease of running your Samza jobs. I'll talk about all of these areas in some detail. So first, faster onboarding. Onboarding is all about getting you up and running with your Samza jobs as quickly as possible, right? So we've recently, with the 1.0 release, completely redesigned the Apache Samza open source website and rewritten almost all of the documentation from scratch. And our goals for the rewrite were to provide a good overview of what Samza can do, so you can decide when to use it and how to use it best. And then also to make it very easy for someone new to Samza to ramp up quickly, whether it's through tutorials, through architecture overview, through code samples. We've done a bunch of work to get you started and running faster. Sam just mentioned this, but we also created a bunch of YouTube videos, video series on learning the basic concepts and architecture of Samza. It's about 30 minutes in length total for all videos combined, so it's a great way to learn quickly about Samza and stream processing in general too. This is available on the LinkedIn Engineering YouTube channel. And then we've also added a ton of code samples and example jobs for reference for new features. You can find these samples on the Samza Hello Samza GitHub repo, but they're also linked throughout our documentation now. And some examples of these samples are for Samza SQL, and I'll talk about it in a bit. The new Event Hub consumer, how to write integration tests for Samza, how to run Samza in Yarn and standalone. If you're familiar with Samza, these make sense to you. If you're not, I will talk about this in a bit. So next, let's talk about the programming models in Samza. Right, with Samza, you can write your application in different ways. We'll explore them with a running example. So here's a typical stream processing application, right? Let's say you want to count the number of page views for each incoming member, each member who's visiting your site in 5-minute intervals. So this is to say, in the last 5 minutes for each member, how many views, how many pages they visited on the website, right? So a typical job or a pipeline would look like this. You have your incoming messages in Kafka, right? In let's say a page view topic. You want to repartition it by member ID because you want to do counts per member ID. And by repartition, I just mean rekey it. So messages for each member ID fall in the same partition. Then you want to do some sort of time-based windowing. You want to group them in 5-minute intervals and then do some counts, statistics on it. Then you want to prepare your final data, right? Do some massaging, emit some logs, metrics, etc., and then finally send it out to another topic called page view per member. Right, so this is a basic pipeline. Now, here's how you traditionally do in Samza with what we now call the low-level stream task API, right? First of all, you'd create 2 separate Samza jobs. The first just for repartitioning the input, and the second for windowing. And here's the repartitioner. It's a pretty simple job. It takes in a message, rekeys it by member ID, and sends it to the output topic. And here's the second half of the job. It's a windowing job. It gets a message, puts it in a map or KV store of some sort, keyed by the member ID, increments the count in the interval, and periodically you just flush out all of that data, right? So it's a pretty simple API. Now, this is a traditional per message based API, which is very powerful, very flexible. You have local state as an abstraction, but it's also a little bit boilerplatey, right? Like it's a bit too low level, a bit too close to the metal in a sense, right? So what we've done is in the new Samza high-level API, we've codified some of these common stream processing patterns and then made it into a more friendly, fluent high-level API, which looks a lot like the Java 8 Streams API. I'm sure you guys have all used it, right? So with the high-level API, you can specify what you want to do instead of how you want to do it. Right? And I'll give you an example of this. Right? But what that gets you is lets you focus on creating complex stream processing applications and pipelines more easily, because you can focus on what you want to do, not how you want to do it, not the wiring part of it. With the high-level API, you can easily repartition data, do stream joins, stream table joins, and then do processing time windows and joins. So here's the same application in the high-level API, for example. You get your input, partition it, window it by 5-minute intervals, do some transforms and send to the output topic. This is exactly what you want to say you want to do, not how you want to do it. So in addition to the high-level API, we've also been working on Apache Beam integration. And for those of you who are new to stream processing, Beam is a project from Google, which aims to be the standard data processing API for nearline applications. And it's just the API. You can swap out the runner or the engine underneath the API and run it in Samza or Flink or Google's own Dataflow or many other engines, Spark, for example, right? And it also aims to be a same API for stream and batch processing. So their goal is to be the API and you bring your own engine. And we've been working on the Samza engine for Apache Beam as well. So with the Samza engine, in addition to all the stuff I mentioned, the high-level API, you also get event time processing, right? We're working on it, it's coming soon, but you also get multilingual API. So you can write your stream processing pipelines, not just in Java, but also in Python and in near future Go as well, right? So they want to be a multilingual API. And then you can get even more complex sliding windows, multi-way joins, a variety of broader options for windowing and joins. Here's the same application in Beam. It looks pretty similar to the high-level API. The differences are mostly syntactic, but you have your input. This part demonstrates how you do event time processing by associating a watermark with each incoming message. Then you repartition your input, you you create, like, you split it into tumbling windows, rekey it, and then send it out to Kafka again. Apart from these two Java or programming APIs, we've also been working on Samza SQL, which is a streaming SQL. And that's a declarative API, which is very SQL-like, but you can express streaming jobs with it, right? And along with the API, we've also been working on SQL Shell, which makes it very simple to create new jobs, prototype them, validate them, and then deploy them to production and get them running within minutes. And we are offering SQL as a managed service at LinkedIn. And the focus here is on velocity, to make it really easy to create Samza jobs. And currently, we support filtering, projection, flattenings, some user-defined functions, and then stream table joins. And I'll talk towards the end about what we are working on next. And here's what the same application looks like in SQL. It looks exactly like a regular SQL. The only stream-specific part here is this windowing semantics. Right? And all configuration and dependencies are taken care of for you. There is no code in this application. This is what you write and submit. And you can imagine there's a SQL CLI, you type this into and then hit enter and then just goes and deploys your long-running streaming job. It's hard to get more concise and simpler than this. So to summarize, the new Samza APIs make it simple for you to create complex pipelines, simplify operations like repartitioning, windows, joins. With Apache Beam, you get event and arrival time processing, and then also multilingual APIs. Java or Python or Go if you want to write it in programming languages, or SQL if you want a declarative language. And here's another view of the same stack, right? You can think of it on a spectrum of high level and abstract to low level and down to the message, if not to the metal, right? There's SQL at the top, which is just this statement you submit. There's Beam, which is still code, but it has event time and windowing semantics, and high-level API, and then low-level API. So next area of work for us was easier development, and this was about offering you the right abstractions and tools to get your stuff done faster, right? So one of the biggest abstractions we've been working on is the table API. So those of you who are already familiar with Samza, this is an extension of the existing KV store API. The KV store is a local store. It's typically backed by RocksDB or some similar embedded database, right? Where you can get your data, bring it locally on the machine you're processing on, and use it for adjunct data lookups. But with the table API, we've extended the store abstraction or KV data source abstraction to remote tables as well. Now, this is the same API you use for accessing, for example, Redis or Couchbase or any other remote store as you use for using your local or RocksDB store. And then it offers much more functionality on top of that. So you can, first of all, compose your tables. You can actually have a local store backing your remote store if you want a local cache in front of it. But also for remote stores, it offers more flexibility like async IO for far higher throughput, better performance. It offers caching primitives. It offers rate limiting out of the box. And it offers retries. So it basically abstracts away a lot of the nitty-gritty and how-to of the remote access behind the API and lets you focus on what you want to say. And the reason it's very useful is for stream table joins. So here's an example of why stream table joins are useful, right? This is a pretty common pattern in stream processing. You have an incoming event, like incoming stream of events, let's say page views. And for each page views, you want to do something very simple. You want to look at the viewer of the page and add some more details about that person to the event, right? You want to decorate or enrich the event with the viewer data. So you can either, there's two ways to typically do this, right? You can either just access your remote member database, could be through a RESTful service, or could be just a direct database read on your remote data store, and then like join the two data sets and then send it out to the output. Alternatively, another common pattern is to use change capture from the member database or remote database and bring the data locally to the local KV store, right? So you kind of, at LinkedIn we use Brooklyn for this, but you can imagine having an asynchronous consume of the stream of changes going to the database, and then just building a local cache of that database. The table APIs makes both of these abstractions very easy. When you're using it for remote IO, like I just mentioned, it brings you features like rate limiting, async IO, and caching. And rate limiting is very important here because in a a streaming service can, or a streaming framework like Samza can process messages extremely high throughput, typically much more than what your database or RESTful services can take. So you need to throttle your jobs, rate limit your jobs so that you don't DDoS them, right? So you get that out of the box. You just specify some configuration and you're done. You get async IO. You don't have to do anything. You just use the async IO APIs, and then everything is much more efficient for you. And then caching plus retries, which is general concern for remote data access. And here's a code example of the other pattern I talked about, right? Where you consume your input, send it to a local table, which in this case is a RocksDB-based local table. Then you just get your input stream, and then join it with the remote table, well, with the local table that has a copy of the remote data, and then you send it to decorated page view event topic. So the other feature, the next feature I'm going to talk about addresses a long-standing pain point for developing Samza applications, which is configuring them, right? Samza has so many capabilities, it's sometimes easy to get lost into all the details it can offer. And also there's the problem of discoverability. A lot of people don't know about what Samza can do for you, right? So we've done some work to make it easier to discover and configure your jobs in code. Now you can, this is the part we saw earlier, right? But now you can describe your inputs, outputs, your clusters, destinations, local tables, all in code using a Fluent Builder-like API. Now you have all the benefits of your IDE, code complete, Java doc navigation, discoverability within your IDE, and you don't need to go back and forth between some properties file and your code over and over. And also, this is another popular request from Samza users. We've added a way to test your stream processing applications against in-memory data. So typically, like before this, it used to be that if you want to test your application end-to-end, you'd bring up a local Kafka, a local Zookeeper. If you're running in Samza Yarn, you'd bring up a local Yarn, and then you'll have a whole integration test pipeline set up just to test your simple application. But now you can just use our test framework to create your in-memory data sets and then run your job and assert on the outputs. And this works for both high-level and low-level API applications. There are several examples for this in the Hello Samza repo, like I just mentioned. But here's a quick example of what the test looks like. There's nothing special here. It looks like just like a JUnit unit test, which is, there's something we said about that. You generate your mock data. You configure your inputs and outputs using the descriptors I just mentioned. You start your application, and once it's done, you just assert that your output contains your inputs in the same order that you specified, right? And I didn't find a better place for this slide, but I think this is very important to mention. Samza also supports running your application both in nearline and offline. Right? So you can take basically the same application code that you wrote earlier, change your inputs from Kafka to say HDFS, and you can run the same application in Hadoop as an offline processing job. And this is really useful when you want to run stuff. For example, if you have a machine learning pipeline and you want to validate your pipeline against some offline data, you can take that code, run it in Hadoop, do some experimentation, validation, do some grandfathering for your data, and then just bring it back nearline when you're satisfied. And this is with zero code changes. You just change your input configuration a little bit. So the final theme that we were working on was around operability for your existing applications, right? And we want to make it effortless to run apps at any scale, and we want to make it cost effective. So as a recap, there's two modes you can typically run Samza in, what we call Samza as a service. And at LinkedIn, we run it using Yarn, where we use Yarn as a multi-tenant, fully managed cluster. We use Yarn for failure handling of containers. If your Samza jobs containers go down, Yarn just restarts them. The cluster is oversubscribed, so we can pack more containers more efficiently. And then we have a bunch of optimizations around state management there. And then we offer multiple dashboards and metrics and monitoring and logging out of the box. Right? That's the first way you can write as a service. But if you just want to use stream processing in a couple of applications, or if you want to run Samza as a library within your application, you can use Samza standalone. Right? This lets you embed them event processing logic within your existing application. So you manage the application, you manage the deployments, you keep it up and running, but Samza works in the background to do stream processing. And typically you use Zookeeper for coordination to do work distribution. For example, if one of your containers crashes, Zookeeper will reallocate the work to some other container. So these are the two modes that Samza can be run in. So for Samza as a service, we've been working on operability improvements. And we've talked about some of these in our previous Streams meetups. For example, now we can provision dedicated clusters within our Yarn cluster for some of our biggest users. And what this gets you is guaranteed capacity. So now you're not contending with other users in the general pool. If someone launched a stream processor with 2,000 processors, it's not suddenly stealing your capacity. And this gets you isolation from noisy neighbors. So you can think of like if there's some other machine, if there's some other containers on your machine that are using too much CPU or too much memory or too much network, then you don't need to worry about them. You just run in your own dedicated cluster. And we do this using a combination of Yarn queues and node labels. And we've also, in the same vein, added support for heterogeneous clusters. For example, now we have clusters that offer SSDs or HDDs, right? For stateful jobs, it's very useful to have SSDs. You need the performance, but they're more costly to run on. So now you can run on spinning disks if you don't have local state, and that's the cheaper option to run on. In future, we're also going to add support for example, GPUs, where if you want to do some machine learning or inference or scoring, you can run on machines with GPUs. And if you need any more information about this, you can look at the talks from the previous meetups, or you can just reach out to our SREs. I'm sure they'll be happy to share their Yarn lore with you and go in great depths about why they love Yarn. Cool. Another improvement we've been working on is around monitoring and debugging your application. We're calling it Samza Diagnostics, right? And you can think of it as error analysis for your application. If you have some diagnostics turned on for your jobs, you can get like, various statistics about your job health. For example, last n errors or the topmost frequent errors. You can have a UI to navigate around exceptions. You can click around and see what the details of these errors are. And then you can get more detailed job history as well. I put it here instead of the what's coming next section because this is very exciting. Most of the work is there. We are still working on open sourcing the CLI and the backend for making this usable, but it should be coming soon. Well, speaking of coming soon, so I've broadly tried to categorize all the work we're doing in the same 4 categories. For faster onboarding, we are working on improving how Samza handles memory to make its memory usage both bounded and predictable. So one of the common pain points during deploying any service or any real-time application is tuning the memory requirements, right? If you take too much, it's inefficient. If you take too little and you run in a containerized, if you take too much and you run in a containerized environment, the container environment will kill you. And if you ask too little, you'll run slowly and more inefficiently than you need to. So we're trying to make it such that you can have a more predictable estimate for how much memory you need, and then Samza will work with whatever you give it out of the box. And we are also just adding and improving our documentation and examples as we work on new features. In terms of APIs, we are working on a few different things. We're working on an async API for high-level API. That's a mouthful, right? The last remaining gap between the high-level API and the low-level API has been traditionally the support for async IO, right? Low-level already has the async stream task, but high-level has no equivalent. And we've been working on this, and we're very close to finishing this. So you'll have this very soon. We're also working on the Python API for Apache Beam. So you'll be able to write your stream processing jobs in Python, which is very popular for machine learning, data processing use cases. And for Samza SQL, we've been working on adding windowing, stream joins, and nested data support. And here's some Python code for you in Beam. It's the same application, but in Python. I'm sure you've seen the map, repartition, window, send to many times by now. For easier development on the table API front. We'll be open sourcing a Couchbase table implementation soon, both for using it as is and also as a reference for how to do your own table if you have a own data store in your company. And we'll be working on batching for remote tables. So we have the caching layer, and the async layer, but we're working on the batching layer still. And finally, and this is a laundry list of things. Well, it's a long list of things, but all of them are very important. We've been working on a few operability improvements as well. We've been working on a new checkpoint tool or a new version of the checkpoint tool, which will make it even simpler to set checkpoints or manipulate checkpoints for your running jobs. So current checkpoint tool works fairly well, but it's a little clumsy. You have to find all of your existing checkpoints, change what you need, and write it back. But this will let you specify your system, stream, and partition level checkpoints at whatever granularity you want. And also, more, very interestingly, it'll let you do time-based checkpoints. So if you're using Kafka, you can say, I don't want to checkpoint to this particular offset, just take me back by 20 minutes. That's pretty interesting. We've also been working on, under the hood, improvements for local state restore and restore performance. We've done a bunch of optimizations around this, and now the restore times are up to 60% faster than what they used to be. So if you have local state and your container dies, or your machine dies, and your container moves to a new machine, it'll take up to 60% less time to restore your previous state. We've also been working on a feature called standby containers or hot standbys, where you can reduce that restore time from not just 60%, you can just reduce it to a few minutes by having spare containers that are constantly replicating data in the background. And as soon as your current container fails, we just swap over to the standby container and bring up another one in the background. We've been also working on supporting host affinity for standalone. So currently it works best in Yarn, but with the new upcoming 1.1 release, it should work in standalone as well. Now Zookeeper will, when we use Zookeeper and do task assignment, will take care of allocating the tasks in a way such that we retain your locality. And finally, we'll be also working on variable local state. This is another popular request. People want to see what's in their RocksDB store, primarily for debugging. Like, I had a stream table join, but my join had a miss. I want to look into my store. Where's my data? You can currently do this with some tools, like some command line things, log onto the machine and look at it. But we'll be working on exposing all of this data to an external system so you can query it in real time. So that's what I have for today. I want to leave you guys some time for question. And yeah, thanks to everyone who's been working on Samza 1.0 to make it awesome. And you can visit us at any questions? No. Okay.
Yes, so I've got a couple questions. I was wondering, could you go back to your the table join one example that you had? Yeah, could you speak a little bit about what's actually going on when you merge the stream with a more static table? And also, can you speak a little bit about your consistency availability model, or how you think about how you partition that space?
Two ways to do stream table joins, right? One is against a live data source, like a remote service or a remote database, right? The other way, typically what we've encouraged for performance reasons, is you do change capture on your remote table, right? So you get a copy of that data sent over to your stream processor, and the stream processor builds up a local cache of it. It's eventually consistent, so you eventually have all the data, right? But the data is also partitioned the same way your input is that you're joining on, right? So the data and the table are co-partitioned. That's why the repartition is such a common operation as well. So if you lose a remote table, you can just access the remote data as is. It doesn't need to be partitioned. All of your processes access the same remote data, or it's partitioned independently, right? The routing layer for the database takes care of the routing. Alternatively, you use some change capture technology and bring the data locally. But the major point is, so if you need strong consistency to some extent, you use a remote table. And if you need eventual consistency, you use the local cache. Typically, it's good enough. Yeah, so did that answer your question?
Sorry, so related to that, so is there overlap in, so if I understand correctly, you're getting a snapshot of your database at that time and then using that passing to your stream processor. So is there a overlap, or is it just discrete separated windows? Should I think of it separate snapshots that you process?
So typically it's actually not a snapshot. You can think of it as the write ahead log for your database is being piped to the stream processor through a stream, right? So as each update happens in the database, an event gets updated or sent to the stream processor, and in the background, it's consuming it and building its local index, right? So well, yeah, it's not like you're doing periodic snapshots and updates. It's just you're capturing the change stream of the database.
Sorry, one more question. Can you talk about a little bit about your scalability and what you guys made to do it more scalable, and what kind of bottlenecks you faced?
Right. So there's a bunch of improvements or optimizations we do around local state. First of all, like I mentioned, the state is partitioned. If you bring the state locally, typically it's co-partitioned with your inputs, right? So you want to partition it such that it doesn't exceed the capacity of any one, or capacity or disk quota of any one stream processor, right? So you repartition it enough. That's also why I mentioned the local state performance, local state restore performance improvements, right? So when we bring the state locally, we actually also write it to typically Kafka as a change log, as a write ahead log for the local state itself, right? So when your container, if it dies and it starts on the same machine, that's great. We'll just use the previous local state you have. It'll resume consuming from the previous checkpoint for the change capture stream. But if it moves to a new machine, we just rebuild the local state from the copy in Kafka or whatever like change log topic you have, right? Which is why the restore times matter that much. Now, we've done a bunch of work to make it faster to the restore if your data is in Kafka, as it traditionally is. But we've also worked on, for some applications, you can't even tolerate tens of minutes of downtime. They need like a few minutes of downtime, right? So they are okay with the extra cost of running, kind of doing the backup, doing the restore in parallel on a different machine. And then we take care of, if your container goes down, we'll just reschedule it on the machine that already was backing up. So that's much more up to date. And that's what we call hot standby.
First of all, congratulations for the great work. And I have a question about the testing framework. You said you improved it so that the integration tests could be done by isolating the service without connecting to other downstream, upstream services. So, and also, my question is, you're using mock data. So how is that different than unit test? And how can we consider it as a integration test?
So it's kind of somewhere between a unit test and integration test, right? Because you use in-memory data, but you actually run the whole Samza container. It's not just testing your application logic, right? So it actually goes through the entire pipeline of consume from a consumer, go through the run loop, dispatch to the like application code, and then write it back to the consumer or to the producer. So in that sense, like if for a simple example, it for hundreds of milliseconds or seconds instead of just milliseconds. So in that sense, it's an integration test, but it's not an integration test in the sense you don't need to bring up anything to run this. It's similar to unit test in that sense.
So you mentioned the standby containers for deployment, or sorry, not for deployment, but for a container failing. I was wondering if you're also looking into doing standby containers for deployments to just switch one over to a new version.
Clarify a little bit. The context here is in Yarn, when we do job deploys, typically when you want to deploy a new version, we bring down the entire job and then we'll start up the new version. So there's some downtime there for applications. It's typically small, but it can be of the order of minutes. So the question is, what are we working on, or are we working on canaries or rolling upgrades, as it's typically referred to? The answer is yes, but it's still early. So yeah, just watch out for more on that front.
Great questions. And thank you, Pratik. Great presentation.
Everyone again.
Our next speaker is Shunping. Chunping is a staff engineer at LinkedIn. He's working in the data pipelines team. And prior to working in the data pipelines team, he built the messaging product for LinkedIn. Today, he's going to talk about Kafka Mirror Maker and how and why we replaced Kafka Mirror Maker with Brooklyn. Right at LinkedIn scale, we hit some unique issues with Kafka Mirror Maker, which made it hard to operate, and we made a call to replace it with Brooklyn. And Chunping is going to tell you all about it.
Hello, can everyone hear me? So hi, I'm Shenping from LinkedIn Data Pipelines team. Today I'm going to introduce Booking Mirror Maker. Booking Mirror Maker is a new Kafka mirroring solution inside LinkedIn. I'm going to talk about why we move away from Kafka Mirror Maker to this new solution and how Booking Mirror Maker help LinkedIn to scale. So here's the agenda today. I'm going to first talk about the Kafka mirroring use case within LinkedIn, and I'm going to talk about some changes we have seen with Kafka Mirror Maker. And then I'm going to introduce the Booking Mirror Maker. So what's the mirroring use case within LinkedIn? LinkedIn is a professional social platform with more than 500 million members. Essentially, we have lots of members on site and generate lots of Kafka tracking data. So those data are scattered around different data centers, and we use Kafka mirroring to aggregate all the data from all data centers together. So that's our main use case for Kafka mirroring. We also use Kafka mirroring to move data between LinkedIn to external cloud service, such like Azure. That means the Kafka mirroring use case is tightly coupled to the volume, the total Kafka volume we've seen inside LinkedIn. In fact, we see Kafka data in LinkedIn grow very fast, and then right now we are at 5 trillion messages and more than 1.4 petabytes per day. So that's a huge amount of traffic. Among them, there are 2 trillion messages need to be mirrored every day, and we have more than 40 Kafka source clusters scattered around different data centers. Essentially, we need to create more than 100 mirroring pipelines from source to destination in order to support all kinds of mirroring. So that's a big number to operate. And how do we achieve the mirroring? In the past, we used Kafka Mirror Maker to do that. And we have seen some issue with Kafka Mirror Maker. So what's the issue? Let's start with the topology. So each Kafka Mirror Maker pipeline mirrors exactly from one source cluster to one destination cluster. And each Kafka Mirror Maker pipeline needs to have its own Kafka Mirror Maker cluster. Essentially, that means if we increase the number of Kafka source cluster, if we increase the number of data center, we need to create more Kafka mirror cluster in order to mirror that pipeline. So we found that the number of Kafka mirror cluster is equal to the number of data center times to the number of Kafka source cluster. In the case for LinkedIn, we need to operate more than 100 plus Kafka Mirror Maker cluster. So what's the problem with more than 100 Kafka Mirror Maker cluster? Let's say there's a developer create a new topic and he wants this topic to be mirror. Okay, let's say we want to add that mirroring, we want to whitelist that topic in a particular pipeline. Okay. Since a Kafka Mirror Maker cluster may have many hosts. And for Kafka Mirror Maker, all the thing is statically configured. That means if we want to add a new topic, we need to modify the config, redo the deployment for every host. Yeah, so that becomes an issue, right? And what's worse, let's say if you want to add for more than one pipeline, want to have this new Kafka topic mirror around all the pipelines. Remember, we might have more than 100 pipelines inside LinkedIn, so we end up to deploy to every host in order just for a single topic, in order to add a single topic. So that actually become a disaster. Yeah, we basically need to deploy just for some small changes. Okay. So that's the Kafka mirror maker pain point we have seen. Also, sometimes our SRE needs to speed the pipeline to isolate some issue. And in the case for Kafka mirror maker, again, it's a config change. We need to deploy around. Yeah, and it creates a disaster. And also, we have seen other issue that one bad partition will bring down the entire pipeline. So, for example, let's say we have a pipeline with 1,000 topics, okay? And a single topic, there's a single echo issue one topic in the destination side. Then the producer to that single topic actually fail. What happened in Kafka Mirror Maker is that single failure will actually bring down the entire pipeline, and it will stop the mirroring for the other 999 topics. So, and the same should happen when we delete a single topic in a destination side. The other 999 topics, also they are theoretically unaffected, they will be bring down by this problematic topic. So yeah, that just become pretty hard to scale, especially if you have 1,000 developers modify the Kafka at the same time. And we have also seen some performance issue. Sometimes we just see Kafka Mirror Maker unable to catch up with the traffic, and there might be some rebalance storm, and we see the lag keeping increased. So what's our solution? I'm not sure if anyone familiar with Kafka Mirror Maker. So what's your solution to this issue? Acho?
You're my solution, man.
Okay, so actually before booking Mirror Maker, our solution is to restart the Kafka Mirror Maker. So we actually create a service to periodically start Kafka Mirror Maker, or it will also restart when we see some lag increase, or basically it will keep restarting the service for any unknown reason. Yeah, so well, that's the solution, but I don't think everyone likes this solution. Yeah, and of course, we don't want to use this solution going forward. That's why we have this booking Mirror Maker. Okay, so what is booking Mirror Maker? So what is booking? Booking is a streaming injection service in LinkedIn. Essentially, it can transport data from source to destination. The source can be something like a data store, can be a database like Oracle, MySQL, or even Espresso. And it can also be messaging system like Kafka, Microsoft Event Hub. And the same for destination, it can be a data store, and it can be a message system. So essentially, Booking Mirror Maker is one special use case for booking. Yeah, so in the case for Booking Mirror Maker, the source will be Kafka and the destination will be Kafka. Again, Booking Mirror Maker is built on top of Booking, and with Booking, it is able to provide better operability, and it can do some sort of photo isolation, and we also optimize Booking Mirror Maker for performance reasons. And one thing which is most important is Booking Mirror Maker has fully replaced Kafka Mirror Maker in LinkedIn. So why Booking is easy to operate? Let's start with the topology again. So this is a recap for Kafka Mirror Maker. In Kafka Mirror Maker, we need exactly one cluster for each pipeline we want to mirror. And if we increase the number of source cluster or number of data center, we need to increase the number of Kafka mirror maker pipelines, or I mean the number of Kafka mirror maker clusters. So that's the case for Kafka mirror maker. But in Brooklyn, we just need to have one cluster per data center. So I think the picture here is too simple. So let's make it more complicated. Oh, okay. If we increase the number of data center and if we increase the number of Kafka cluster, you can see Brooklyn Mirror Maker can greatly simplify the number of clusters you need. In fact, in second thing, with Brooklyn Mirror Maker, we are able to bring down the cluster we need from more than 100 plus Kafka Mirror Maker cluster to around 10 Brooklyn Mirror Maker cluster. So here comes another question. Okay, somebody may say, okay, you reduce the number of mirroring cluster, but if you need to do deployment every time you change a configure something, then still reducing the number of clusters doesn't seem to solve the issue much, right? So that's why we come up with this dynamic management API in Brooklyn. So in Brooklyn Mirror Maker, we use Zookeeper as a meta store, and we store metadata layer. And we also provide a RESTful API to allow users to create, update, or post, doing a bunch of things around the pipeline. So here is an example. Let's say we want to create a single pipeline. We want to create a mirroring pipeline. Okay, we just need to specify the source and destination, and then we issue a HTTP RESTful call. Then that's it. No need for deployment. And again, if we want to add another topic on top of it, we just need to issue an update. There's no need for deployment. In this case, I want to add more topic. I want to add topic C and topic D into the mirroring. I just need to issue update command and then change the source, and it's an HTTP RESTful call, and we don't need to do any deployment. Moreover, we can also subscribe to Regis thing. In this case, we don't even need to issue a HTTP update command. So that becomes much simpler to operate. Also, Brooklyn also provide API like you to pause and resume mirroring pipeline. Besides this manual pause, Brooklyn Mirror Maker also detect fault for you. So what happens is, let's say if there is an error in a particular partition, Brooklyn Mirror Maker will automatically pause the mirroring for that particular partition, but the other healthy partition will continue to work under Brooklyn Mirror Maker. And the Brooklyn Mirror Maker will periodically check if that partition becomes healthy again, and it will auto-resume the partition for you. So here comes another question. Brooklyn Mirror Maker is pretty powerful. It allows you to pause, resume pipeline, and it can also do automatically pause for you. So it's getting complicated, right? Because if, let's say, if you have lots of topic, you have lots of topic and partition to mirror, how do you know if this topic is paused, or if this topic has some issue and it is paused by Brooklyn automatically? So actually, we have the same question here. So that's why we come out this diagnostic API. This API basically allows you to get all the status for all the status of the topic within that pipeline. So with this command, we are able to get the assigned topic and the partition which is auto pause, and we can see the reason that why it get auto pause. Yeah. So with those API, that make Brooklyn easy to operate. Now I'm going to talk about some performance improvement we have done for Brooklyn. So here is the mirroring pseudocode. Essentially, what we do is we consume record from Kafka consumer and we'll produce it through Kafka producer. And periodically, we do a producer flush to clean out the data from the producer buffer, and then we'll commit the offset back to the broker. And we discovered that the producer flush can be very expensive. In some cases, it can actually take several minutes to do that. So we want to get rid of it. That's why we come up with this flushless produce. Essentially, we don't want to do flush, but still we need to commit the offset, right? So we use a producer callback to acknowledge the offset, and we create something to manage the offset. So that's how we do it. We create something called checkpoint manager, and it will memorize the acknowledge point sent by producer. So let's say we send a message 01 to, after producer send a message 01, producer will send a callback contain the offset of that message back to checkpoint manager, and checkpoint manager will keep memorizing it. And if we find out the in-flight message is actually newer than any message we have memorized for, that means we can safely commit that offset. So in this case, the 01 and 02 has been acknowledged through the producer callback, and the checkpoint manager figure out like the new message 03, 04 is newer than 01 and 02. Then checkpoint manager will safely commit the offset 02 back to the broker. So in this way, we can get rid of flush. There are also other performance enhancement we have done for booking. So in booking, we use data stream tags to control the number of consumers we want to use for a particular pipeline. So a data stream tag will have a dedicated Kafka consumer, and it will use a shared producer pool to produce the data. And for different pipeline, we can configure with different number of tasks, and then we can allocate, we can map the tasks to different hosts, and we can tune, essentially we can tune the throughput for each pipeline. And one thing Brooklyn Mirror Maker does is Brooklyn Mirror Maker use sticky assignment for this task to speed up the task allocation. So here's the example. Let's say we have originally 4 Brooklyn Mirror Maker hosts, and we have 6 tasks here. And there's another host coming up. Brooklyn Mirror Maker will just reassign the delta. In this case, it only reassigns task 6 to the new Brooklyn Mirror Maker host, and it doesn't change the assignment for other remaining hosts. So basically, you want to minimize the change if we bring up the host, and with that sticky assignment, it will allow Brooklyn Mirror Maker to come up in a short period of time. And here's some performance number we got from Brooklyn Mirror Maker. In our test environment with 20 data stream tasks, we can see the throughput increase, go up to 28 megabytes per second. The memory utilization is around 70, and the CPU utilization is pretty high. It's almost 100%. So some people may have this question. So ideally, mirroring is transporting data from source to destination. It shouldn't do any complicated logic. It doesn't need to do any aggregation. It doesn't need to even look into the data. So why this mirroring will need so much CPU? Why is it CPU bound? Yeah, this is actually a very interesting question. We did some profile, and we found out that actually 70% of CPU time is spent in decompression and recompression in Brooklyn. So why is that? That is because Brooklyn using Kafka producer and Kafka consumer, and Kafka produce Kafka producer will actually compress the data before sending out. And the same case for Kafka consumer, it will need to, Kafka producer will compress the data, and the Kafka consumer will decompress the data, yeah, when it consume. So yeah, that's the case for Kafka consumer. But for the case in Brooklyn, because we are doing mirroring and we don't need to look into data, such a thing should be avoided. So that's why we come up with this path-through mirroring. We basically want to skip the decompression and the recompression. With that change, the throughput can go up to around 100 megabytes, which we believe is reaching to the theoretical limit of that host. Basically, there's a network bandwidth limit for each host, right? 100 megabytes is equal to 1,000 megabits per second, and it's approaching to that limit. And the CPU utilization dropped to only 50. So that's the work we have done for Brooklyn. And then again, there are some works we plan to do, but we haven't done yet. So I'm going to talk about some future works too. So we actually have seen some issue in workload allocation. So some hosts may just happen to be assigned with very hot topic, and the other hosts may be assigned with some color partition. So the CPU utilization is not equal. So in the future, we want to do a workload-based assignment. Basically, we want to detect the throughput for every partition, and we want to mix hard partition and cold partition together to get a better utilization of our resources. And then another thing about performance we want to do is we want to do auto-scaling. We basically want to adjust the number of Brooklyn tasks automatically based on the throughput. So in that, basically, we'll hope in the future you can just create a Brooklyn. You don't need to specify the number of tasks, and the Brooklyn mirror can automatically detect the throughput and do the magic for you. So that's it. And one question you guys might have, okay, you talk a lot about Brooklyn, and how can I get it? Well, LinkedIn open source that. So the answer is yes. LinkedIn is going to open source Brooklyn next month. Yeah. Oh, come on. So any question?
Hello. Hey, first, nice talk, and glad to see that end of month Brooklyn is going to be open source. I have 3 questions. So 2 is related with the comment on the Kafka Mirror Maker. Can you elaborate why one bad partition on the destination will just bring down the whole pipeline? What is the reason? And
so essentially, I don't think Kafka Mirror Maker doing any fault isolation. So I mean, I'm going to talk about the difference and what we have done in Brooklyn. So essentially, Kafka Mirror Maker, everything is shared. Everything, if that partition is shared by the same consumer, and they basically didn't do any fault isolation on that. But for the case in Brooklyn Mirror Maker, we isolate the error to a partition level. So basically, we'll see if there's an error happen, if there's an error happen for that particular partition, we will only stop that. We'll memorize that partition and we'll stop only for that partition. We basically tell the broker to stop sending for that partition only.
Okay, so that means inside the same consumer client library, you call the pause on the bad partition.
Yeah, that's right.
And your checkpoint manager also is managing the checkpoint per partition in that case.
Yes,
right?
that's right.
Okay, I see. Okay, that answered my second question as well. Okay, thanks.
Okay.
A question about when you mentioned that you're moving from mirror makers into just one Brooklyn, it seems that you're just pushing the aggregation point higher That is, the aggregation point was already sort of like merging the streams together in some sense, correct? So in that sense, can't you also push the aggregation itself higher as opposed to do mirroring at all, so that you just do the logic in Brooklyn? Then you don't have to worry about the compression as much.
Sorry, I don't understand your question.
Okay, if I see the architecture progression,
Yep.
you had Mirror Maker, which was basically, I think of just as a queue, right?
Yep.
Basically queuing stuff. And then eventually those points will be aggregated by aggregation point, correct? So now if you think about it, then if you had n things going into the aggregation point, essentially Brooklyn Maker is sort of like pulling all those streams together and putting into one out, correct?
Yeah.
So you might as well move the aggregation point up, because that seems to be the location that Brooklyn would be merging the streams together anyway. So maybe I'm misunderstanding. Why not just do the aggregation in Brooklyn?
So I don't understand what do you mean by pushing the aggregation up.
Okay, go back to your mirror. Yeah, here's here. So if you go back to your Mirror Maker one before, go to the fine here. So you can see that the aggregate tracking, the box that you have for aggregate tracking, right?
Okay.
It's sort of merging two streams, correct?
Yes.
The left.
Yeah.
So now if you look at the box to the right, essentially you're aggregating it at BMM, correct?
Well, that.
Well, not aggregating. Actually, misnomer. You're actually just merging those two streams together at BMM, correct?
Yes.
So my question is, why not just move up your aggregation to BMM, because you're merging already two streams, right?
Oh, but the way we merge that is to basically produce them into a single destination topic. So let's say we have a topic from the tracking in data center A and the tracking in data center B. The way we do aggregation is to push into the same topic in the same topic in the aggregation tracking. Yeah.
Well, my point is, why not just do the aggregation at BMM as opposed to like make a mirror? Because you already had CPU bound by decompression and compression. Won't aggregation be just much more compression for you? You don't have to do extra passing stuff around.
But let's say if we move the larger, we still need to use Kafka consumer to consume the record, right? And in this case, we cannot save the decompression and recompression. So that means that actually we'll consume more CPU here. Yeah.
Maybe to clarify is that we don't do aggregating data. We are concatenating together. So there is no processing or aggregation or like counting like we saw in Samza with window. We basically have events in both trackings, and we want to have a new topic that have both events. But there's no data aggregation itself, just putting it together in the same topic. So that's why it doesn't make sense. So the number of events in the one in the bottom will be the sum of all events in the top. So there's no advantage of doing what you mentioned, because that's what's the confusion with the term aggregation.
I have a question here about the performance. So in your final experiment, it shows that your cluster is relatively small. So in your beginning, you said your KMM from 100 cluster becomes the BMM 10 clusters. So I'm just curious, because it just compare the cluster. It's not an apple-to-apple comparison. It's possible your 100 KMM is smaller, but your 10 BMM is large, right? So did you compare the cluster-wise or data center-wise, what is the generalized resource that the BMM can save, and the SLA is guaranteed compared with the KMM? Do you have those data?
So I think the number here is not mean to compare about the performance. It's mean to show how Brooklyn Mirror Maker make the operation easier. So yeah.
Yeah. It's possible that your KMM is 10 times smaller. KMM cluster is 10 times smaller, right?
Yeah.
So then this comparison make people confusing.
So right now, unfortunately, I don't have apple-to-apple comparison, or I don't have the cluster side from Kafka Mirror Maker. But in our case, the I mean, I don't have the exact number, but based on our experience, the number we need for Kafka Mirror Maker, I mean, for the cluster, are reduced after we migrate to Brooklyn Mirror Maker. Yeah, but I don't have a good sheet to do an apple and apple comparison because maybe maybe we just save the resource because not because of performance, but because we can allocate more pipeline, we can share more consumer together in same single machine. Yeah.
Yeah,
So,
you definitely hear BMM has a contribution for sure. I'm not questioning you. I'm just showing this slide. I mean, cause confusion.
Yeah, but this slide means to show like Booking Mirror Maker can consolidate the resource together, and it will be easier to operate. Yeah.
Thank you.
Sorry, last question, like regarding to the pass-through. So when you say you avoid the decompression and recompression in the pass-through, then are you assuming that the source and destination topic are basically the number of partitions are the same?
Yes, the number of partitions need to be the same between source and destination.
So it's identical topics.
Yeah, yeah. Okay, cool.
Thank you, Shenping.
Thank you.
Just to answer one of the questions around perf comparisons, there was a comparison done between KMM and BMM, but we just don't have the data in the slides, right? But if you are interested, we can share it with you at a later time. So we'll take a 5-minute break, or probably 6-minute break, and assemble back at 7:50 p.m. Our final speaker is from Facebook. So we'll have Ritin from Facebook talk about Puma.
Yeah.
Our final speaker is from the Facebook real-time streaming team. Ritin has been in Facebook for the last 2.5 years. Prior to that, he worked at Salesforce. He contributed to the Apache Bookkeeper project. And prior to that, he was at NetApp working on file systems and replication. He's here to talk about Puma. Puma is a SQL-like language for stream processing. And he's going to share his experience of running and building Puma at Facebook. And as you would all know, Facebook is known as one of the few companies that builds really cool infrastructure. So I'm really looking forward for this talk. Thank you.
Thanks, Amit. Yeah, thanks for having us here. Yeah, my name is Ritin Shetty, and so today I'm going to talk about Puma. It's our declarative stream processing service, and it's a managed service. So before I go more into Puma, just want to know, have people heard of Puma? We have published some papers. Okay, not bad. But I think there's not a whole lot about it. I was just searching myself, what have we done in the past about Puma? And I saw a talk from like 2011 or something, when it was like the early days of Puma. But I think we've come a long way from there. So yeah, I'll talk more about what Puma is and how we use it and what we have learned from running it as a service. So just to be clear, this is not the only stream processing system we have at Facebook. We also have a couple of other frameworks. They're called Stylus and Swift. So they are frameworks and libraries, and the people are expected to use, know how to use those libraries. They're usually in C++ or Python, and so people have to make use of those libraries and implement their apps on their own and manage it and deploy it and all that. So it's not; those are not offered as a service. But we do support those libraries. But Puma is a service wherein the interface is an app written in a SQL-like language, and once the user writes this and gives it to us, we take care of running it. and the user doesn't have to deal with the day-to-day operation of the app. So that's what I'm going to be talking about today. So this is the agenda. So I'll go a little bit into the use cases of Puma, what people use Puma for. So I'll talk a little bit about the language, how do you write a sample Puma application, what are the features we offer in the language. Then cover a bit of the microservices around app creation, app deployment, and testing and provisioning. And then go into the operators that, some of the popular operators that people use in Puma. So finally, we'll talk about the SLA model we have and how we, run the service and what kind of SLA we promise to our customers. And finally, we'll talk about our lessons we have learned the hard way, and maybe some of you run such systems, so may be able to resonate with that. So Puma, as I said, has been in production for the last 7+ years. It's one of the early, streaming service that used SQL, I believe, and it, uses at least one processing semantics. So in terms of scale, it's pretty big service. Across all the Puma apps, the amount of data we process is in the hundreds of gigabytes per second. Thousands of apps running in production, and it's used by hundreds of teams across Facebook. It's quite big. So example use cases. So a lot of machine learning engineers use Puma for their stream processing needs. Similarly, there are a lot of services that run within Facebook. If they want to see how their service is running, if they want to get insights into their services, maybe they want to see error rate or things of that nature, they can write a stream processing app and get that info as well. Experimentation is another common use case where you launch a new feature on Facebook and you want to see how that feature is doing. Is it working as you planned? To get real-time insights into that, people use stream processing. Speeding up batch pipelines. So there are a lot of thousands of batch pipelines, data warehouse pipelines that that run every day at midnight when the day when the day ends and when the partition gets created. These pipelines kick off. So it's very important that these pipelines, these tables, they land on time. And if they're late, then those batch pipelines start late, and so that has that impacts the downstream pipelines. And so it has a so that's why some of the critical tables we run them in we populate them from streaming. So because we are streaming, we can always guarantee that when the midnight strikes, we are ready to close the table in Hive and make it available for the downstream batch pipelines. That's another popular use case. Real-time ingestion into different databases. So there are several key value stores and databases across Facebook, and people want to do some transforms or filtering before they ingest into these databases. So that's another popular use case. So these are some of the handful of use cases that I am aware of. From looking at being on call. So before I go into the details of Puma, so let's make sure that we are on the same page in terms of terminology. So Scribe is our distributed buffered pipe. That's what the Scribe team likes to call themselves. So I believe it is equivalent to multi-region Kafka. So yeah, I'm not very familiar with Kafka, but I think we were able to. The Scribe is able to give us a unified view of a category. Category, I think, maps to topic, by the way. So Scribe is able to give us a unified view of a category, irrespective of where the data, in which data center the data is. And then a bucket is our version of partition of a Kafka topic, I guess. We have categories and buckets. Oops. Okay, okay. So Turbine is our job management layer. It's a stream processing specific job management layer. It's equivalent to Yarn, I think, in the open space, in the open source world. Slicer is our map. We call our mapper jobs slicers for some reason. I don't know why. And shard is our reduce job. These are all historical names that stuck and nobody bothered to change. But I think I should make it clear. So the language, I'll have an example app, so you will see more about how what it looks like. But it is SQL-ish. It's a subset of SQL. It's not ANSI SQL. If you're familiar with SQL, you can work with it. It has standard SQL types like int, begint, long, the booleans and lists and map and all that. And we have rich set of SQL like built-in functions as well. And then we also allow people to add UDFs and we can enhance the set of functions that are available. We also have a linter, which prevents people from making changes to their apps and causing issues to, basically stopping them from, shooting themselves in the foot. We found that to be quite useful. So let's try to create an example Puma app. So we want to count the number of users. Suppose you have a website and you want to count the number of people who are accessing the different applications on that website. So let's say the input category, we call it API hits, and we want to count the number of users accessing a particular app. So we want to do group by app ID, and we want to see the aggregations count and count distinct. How many people use the app and what are the distinct users? How many distinct users want to see the app? And suppose we are interested in 1 hour window, and our event time column is say something TS, and we want to write the output to a category called result. So that's what we want to do. So we start with creating an input table, saying we want to create this input table, and we want to read from this category from API hits. So this is like think of it as you're saying in-memory representation of your category, and when you do this, we get the schema for the category from our metastore, so we don't need to say what are the different columns in that category. So we will figure that out. And then the user says, I want to shard by app ID because I want to do group by app ID, and I want to use TS as my event time column. So that's the input, and then the output column, or output table. So output table says, create the API Unix output table and select app ID and the aggregations. So the group by is implied. So this is where we are not really SQL. We don't have a group by statement. We instead kind of implied. If you're doing aggregations, and then we assume that the first few columns that are not group aggregations are keys, and we do group by them. And you mentioned the list of aggregations, as a comma separated list. And then you specify, this is how we specify our aggregation window. It can be 1 hour, 15 minutes, 5 minutes. And then finally, write the output to a result category. So that's an example app that does, what I said earlier, which is, do some aggregation to calculate the distinct users accessing the apps. Does that make sense? Cool. So okay, how do we provision it? So once the user writes such an app, so the user goes to so we have a portal that goes there and creates the app, and we have a sort of a testing environment. I'll talk more about that in the next slide. Once he does the testing, he lands, somebody reviews the code, the PQL app that he has written. It'll get reviewed, and then he lands the change in the PQL repository. So then we have a microservice called PQL Tailor, so which keeps looking for new commits that are going into this repository, and whenever it finds there's a new app coming in or when an update is happening, So it automatically detects that and does some compilation, converts the PQL into expression, sort of an expression tree, which we later use for creating the jobs, and it stores in our metastore, and then it calls the provisioner. Provisioner is another microservice which, when called and says, okay, hey, go schedule this app, provision this app, and the provisioner then goes to the metastore. The same metastore picks up what was stored there by the PQL tailor, and then goes ahead and provisions it in the production. So this is the entire flow when a new app is created or when an update is made to an app. Make sense? So yeah, so provisioner, as I mentioned earlier, it's a microservice. So its main task is to take the PQL, interpret what the PQL is, and get the understand what the DAG looks like, and then go ahead and create those jobs. So in the previous example, there was an aggregation happening. So there is going to be a mapper job that does the sharding to make sure that the keys go to the right reducer, and then there will be a reduce job. So that's what the provisioner would do. In addition, it can figure out, depending upon the input categories, the input rate. Sometimes the input rate is low, so maybe one or two tasks is enough. But sometimes the input rates are in tens of gigabytes. In which case you need to go create like 64 or 128 jobs, tasks, to be able to consume that much amount of data. And then if there are any, so between the mapper and the reducer stages, we have the input, we have the category persisted, so that there is no need to for the reducer to for the mapper to talk directly to the reducer. We have a intermediate category, and provisioning those are also handled by the provisioner. And then sometimes if you're doing aggregation, so we need storage for fault tolerance, and so somebody has to provision that for the app, and it's our provisioner that does that as well. Sometimes when you do the transformations, maybe your DAG was had like 5 stages, and the user realized that okay, some of the stages are no longer needed, and the app changes that into say a 3-stage app. Then the provisioner detects that and deletes those unused jobs and artifacts that are no longer required. So that's so it's completely automated, and we don't get involved in provisioning an app anywhere. So coming to the sandbox testing, so when you write a big PQL, you're not sure what you wrote is going to do the right thing that you want it to do. So you want to test it, and we provide a sandbox environment. So wherein you take the exact same PQL and run it against some subset of data from Scribe. So if the Scribe category has like 16 buckets, we say in the sandbox we tail only one of the buckets. So it's just sample the data and run the data against the same set of jobs, the mappers, reducers, and so on. So you will get you will be able to see the result in real time, and you'll be able to subject it to the real data that's coming into the categories. As far as the sinks, the output categories are concerned, so we create test sinks for the sandboxes, so that the user, we don't override the prod categories and cause disruption that way. Again, and the user doesn't need to worry about that. Our sandbox, the creation logic takes care of that, and creates the test categories. And once he's done, playing with it, we can get rid of it or keep it for. These are long-running, things. If you're interested in seeing, how it does for over a period of a day or so, just to see that it can withstand the traffic. So you can do that. Sandbox is run. I think we let it run for a week or so before you make it run in production. So this is what an example provision Puma app looks like. Sorry, I had to hide those names because they're not supposed to show that outside of Facebook, but it'll give you a picture of what provisioned app looks like. There is a scribe category from which you start from the leftmost side scribe category. There's a slicer, which is a mapper. It's reading from it, and it's outputting to 2 scribe categories. So these are intermediate scribe categories. Most likely in this app, there are 2 aggregations happening, and the aggregations are using different keys, and that's why you have different glue categories. And then the Puma shards are doing the aggregation, and they're writing the results to a Puma table. And then there's another Puma slicer that reads from those tables, because the output from the aggregation is also a stream. So you read from that and send it downstream. I could only fit this much, but you get the picture. So this is what the user gets to see his app, how his app is deployed, and then if he's interested, he can click on the various dashboards that are there and understand what's going on. So coming to the how we what we do with the PQL. So at a high level, we take the query, the app that the user has written, and we compile them into expression trees. It's like an AST of sorts, and we store that in the metastore that I mentioned earlier. And then the stream processing jobs, the mappers and the slicers and shards, when they're running, they download these expression trees and they translate them into Java classes and then inject them at runtime. The advantage is that the single binary can run any PQL. So if you have thousands of apps, the mapper binary remains the same. It just has to download the required PQL that it's supposed to run and then run it. Okay, so that's about the language and provisioning and so on. So now let's look at some of the operators that that are commonly used. So slicer, as I already talked about, is our mapper operator used for filtering, projection, and partitioning. So map join actually is nothing but the stream join. So we call it map join internally, but map join is also implemented as a slicer. We don't have a separate operator for some reason. But yeah, so that's another function that the slicer does. If you have a lookup table on which if you want to enrich your data from a lookup table, so we can do that as well. So I want to talk about a couple of optimizations that we have done in slicers, which are I think interesting. One is the region local job instance. So just like the previous talk where I talked about data coming into different data centers. So we have the same issue. So we have data coming into different data centers. So this optimization, the goal here is that irrespective of where, so if you have the data coming into a particular data center, we also have an instance of the mapper job running in that data center and consuming that data and then outputting the result. So that way, if you have 10 data centers, so you have 10 instances of mapper running in each region. I'm sorry, one instance running in each region and working on the data that's there in that data center and then outputting the result to the downstream category. So the advantage is that you're saving a lot on the network traffic. You don't need to send data between data centers, and this gives us a lot of savings. I don't have the exact number, but I think it's a lot. Somebody in the team did some analysis, and it was giving us a lot of savings. The other optimization we have is the co-location logic, co-location of app logic within the same slicer. So if you have 4 different apps that are reading from the same input category, so then we don't run 4 different jobs. So we run a single slicer job, and inside that job we process the logic for all the 4 apps. So it's kind of multi-tenancy. Again, this gives us huge savings, especially when we have some categories that are if their input rate is 4 gigs or 10 gigs. So then you don't need to, their savings is multiplies as and when new apps come in. So that's another very interesting optimization that we have implemented. Shard is our reduce operator. As I mentioned earlier. So the input is always sharded by the aggregation key on which you want to do aggregation, and we use the event time that's in the category input category for watermarking. So we support tumbling window aggregations and all the common aggregation functions like count, average, count distinct, approximate percentile. All of those are provided. So we also have a way to read the data that the start is providing using a RPC-based service. We call it read service. So that's one way to consume the result. So if the web layer is interested in getting the data from the shard, that's one way to do it. The other way is to use the Puma tail. So I think this is we saw it in the previous slide where the output from the aggregation was being read by another slicer. So that slicer is called Puma tail because it tails the output from Puma. Because the output from aggregator is also a time series, so we can have a stream processing operator doing that, and we can chain such operators with other slicers and shards. So if you want to do more aggregations, that's also possible. So the next operator is the streaming join operator. So we support ability to join two streams, and this shows how it is done. So we also had a paper on this. If you look up, it was in the last year's BLDB conference. So it goes into the depth of how this was done. But at a high level, so we have a slicer that takes the stream and that shards the data according to the join keys, both the left and right, so that the join operator, when it encounters a key, it can be sure that there's no other task that would be processing that key. And then the output from the join is is written to a downstream category, and then we can have other stream processing operators beyond that. And the join operator itself maintains a window of events from one of the streams, and then from the other stream it looks for a match, and how long it keeps in memory, those are determined by the PQL, what this mentioned in the PQL. Yeah. And yeah, we support left outer and inner joins, and we use fault tolerance for local and remote storage. We use we have fault tolerance for the streams that we keep in memory, so that we don't have to redo any of the work when we crash and come back. Okay, so that's about the operators. So let me talk about Scalar. Scalar is one of our microservices for running it, which is useful in our day-to-day operations. So the idea behind Scalar is that when we have so many jobs running in production, things change. The input for a category maybe was 100 megs today, and it becomes 1 gigs after 1 week or after 1 day, after 1 month, depending upon the popularity of that feature on Facebook or something. And then so then our tasks, what we provision, the provisioner estimates how many tasks are needed based on the input, but that estimate becomes out of date, and then somebody has to give them the more number of tasks to make up for that input rate increase. And we don't want to do that manually, because it's possible to do when you have maybe tens of apps, but when you're running at scale, it becomes hard for our on-call to go manually scale up the tasks. And that's why we ended up creating the scaler, which it looks at the input rate and looks at the lag a particular app is having, and if it is beyond certain threshold, we go and scale up the number of tasks. On the flip side, if the input rate has decreased for a considerable amount of time, then we can scale back and reduce the number of tasks and get some savings that way. It can do the same for memory as well, scale up. Since it's Java, we play with the XMX. We increase it up and down based on if you're seeing memory issues. And if you're late in seeing the memory issues, sometimes you'll see oomps. So then the scaler detects that and goes ahead and increases the XMX for them. Okay, so switching gears, I think that's all about the Puma and its architecture. So let me talk a bit about our SLA model and then close with the lessons learned. So every time you deploy an app, a new app, so we automatically create the alerts for them. The user or on-call doesn't have to do anything. We also create the debug dashboards. In the previous slide, I showed the DAG, where you saw the slicers and shards. So there are links to the dashboards to dive deep into what's happening on each of those operators. So those are all things that gets auto created. And same thing with the alerts. We usually measure 2 alerts per job, so lag and crash loop. We have two alerts per job. Lag is, if it is lagging by a certain amount. So we want to tell the on-call saying, hey, something is going on with this. It's lagging. It may be close to missing the SLA. Go ahead and fix it. Other one is, crash loop. If it is in crash loop for some reason, for whether it is whether it's because of a bug or it's because of a bug in the PQO or whatever the reason may be. So we create a task for that as well. And stream processing team is the first point of contact for all alerts. And we have a very strict SLA for important apps, meaning if these apps are not running if they're lagging for more than 30 minutes or hour, then maybe it's something is going to crash and burn. So we want to prevent that. And so in such cases, for those categories of apps, so we chirp the on-call. So whether it is day or night, on-call has to go and fix that. But then, there are some categories of apps that are, the SLA is flexible. It's not like, you can completely ignore it, but it's not urgent to be, fixed in the middle of the night. So we also create tasks for them, and we do go fix them, but on a more relaxed schedule. Okay, so finally, so what have we, some learnings from running Puma as a service for the last few years. One thing is, it's very important to have automation, having auto remediation for things that that go wrong. When you have thousands of jobs running, you never know what breaks, and if something breaks, you don't want to go fix them in the middle of the night. It would be nice if you have auto remediation scripts or tools that go collect all the logs, but fix them. Maybe all it involves is to restart the task, in which case it does that, but also collects the logs for us to go debug later on. Investing in such things, saves a lot of on-call grief. Bad hosts, when you have so many hosts, hosts go bad for various reasons. And when one host goes wrong, it affects multiple apps. And again, if you don't have the auto remediation for that, then on-call has to get involved and fix the issue. But if you have auto remediation that detects the bad host and kicks it out of the fleet, then you can save yourself a lot of work, manual labor. So being proactive is also important, I think, because we have seen most of the issues comes in when an app is newly created and provisioned. The first few days is when maybe our automation didn't catch everything right. Maybe it didn't provide the right number of tasks, or there was a bug in the PQL logic, and there is some bucket that is too hot because they didn't do the right sharding function. So in such cases, it is important to, I think, have a staging area for the apps, wherein first make sure that it's running fine for a week or so without any alerts, and then once it's been in that state, then maybe promote it to prod. I think that will save a lot of on-call issues, basically maintenance issues, and detecting issues during provisioning is also, I think, very important. That's where, the linters and other things that I mentioned earlier is very important. Reject them at the, reject the bad peak. Well, even though it may be valid to write it, but it may be hitting your constraints. It may be hitting your limits somewhere. For example, we have, when you're doing streaming join, if the stream window join is few hours is fine, but if it's really large, so then it'll affect your join operator. It may run out of memory. So catch that as soon as possible, as early as possible. So backfill is something that that comes up. There will be bugs in our code or in the user code or in our upstream dependency. In which case, the user comes to us and says, can we rerun this job for this much time for yesterday because something was wrong? And we can do it because on Scribe we have some retention, maybe up to 3 days or 5 days, depending upon what they have set up. But we are not set up to do that. We are only set up to run things in streaming. We are not set up to run backfill jobs. If it is really impacting them badly, we will honor that request and we can run it for them as an ad hoc job. But if it is something that is recurring, then we prefer them to run it in batch. So that's where, but if they have to run it in batch, the PQL is not compatible with our batch engine. So we use Presto, Hive, Spark, and so on, and they have their own languages. And PQL, then they have to write they have to translate their PQL to Presto and then run it there. And that's not good either. And when they're in a crisis, they don't want to be rewriting their app. So that's why we are investing in a unified authoring experience. This is for our next generation of, we are investing heavily in that. But I think that's something to be aware of when you're running a service at backfill is absolutely important. Correctness, having automatic data quality checks before we publish the data will prevent a lot of. I think it's important to be correct rather than publish early. We have had cases where we published wrong data and then they came back and said, okay, because of a serve in Scribe or something, only some amount of data came through. The rest is still there, and you guys missed it, and so now we need to redo the whole thing. So that comes to the backfill. But if we had a DQ check, that could have been prevented. We could have caught it before we exported it, and then we could have waited a little longer and before publishing that. So that's another learning. And global watermarking is it's a little complex, but when you have a DAG with multiple stages of operators, it's possible that some stage upstream is lagging and some amount of data is stuck there, but downstream you're not aware of that. Maybe you're consuming from, let's say, 10 buckets, maybe 2 of the buckets are stuck. Data is not coming through because of some issue upstream, and you don't know that. And if you're looking at your own watermark, then you are not aware that what's happening upstream. So having a global view of the DAG helps to be accurate. That's something that we discovered during the through many incidents, and we're trying to fix that now. So Scalar, I think it's a must when you have so many apps, but it also comes with its, it has pros and cons. Sometimes, if the Scalar logic is too aggressive, it can scale up your tasks by a lot, and then that can cause capacity crunch, especially when you have an incident in, say, in Scribe, and things were not coming through, and then all of a sudden it, multiple jobs start getting their data from Scribe, and then everyone says, okay, I'm lagging. So then the scaler goes and scales up every one of the jobs. Then then you run out of machines to run so many tasks. So you have to be careful. You have to have way to prevent that. You need to have some limits on how much you can scale. Same thing with scaling down. If you're very aggressive in scaling down, you think, oh, it doesn't need so many tasks. I can scale it down by maybe half. but again, you can miss that, and then you'll start getting a lag immediately, and then the scaler has to come back and scale it back up. So yeah, so there are pros and cons with having a scaler as well. And then Reaper service, I think when there are so many people using the apps, people leave teams. They forget to delete their unused apps, and then nobody knows that the app exists, and we don't know them because we were not involved in its provisioning, but it is producing data that no one is consuming. So having a Reaper service that detects that is very important. With that, you can reduce the number of apps that you are running. You only run the ones that are really needed, and then also recover capacity. Same thing with the input category. Somebody deletes the input category, but they forget to delete the Puma app that is downstream of it. Then when that happens, we start getting crash loop alerts, and then we go figure out, oh, somebody deleted it, but they forgot to delete. So we have discovered such issues, and we have created Reaper service now. So regarding alerting, making stream processing team the first POC for all alerts, I think it's not a great idea because irrespective of whether the bug is in our code or in the user code, we get chirped, and we have to go figure out that, oh no, this is not our bug, so we pass it on to the user. So it's very important, I think, to invest in, it's not easy. When you have a crash loop, it's difficult to figure out who was responsible, but we are trying to fix that in our next generation of Puma. So job management layer, I talked about earlier. We have our own job management layer for stream processing, which is we had to build our own because the one that we were using before was their SLA was not it was not meeting our needs, because our requirement is that at any time a task goes down, so it's okay to go around, but it should come back quickly, right? It cannot be down for too long. Otherwise, nobody is reading that data from that particular category or from that particular bucket in that category. Then immediately we start getting a lagging alert. But the job management layer that we were using earlier was more tuned towards web. So their SLA was, we guarantee that 99.99 or whatever number of tasks will always be running, but that doesn't mean that one task that is not running will affect us because our requirement is that all of them should be running and should be, if they're not running, if they go down, it's okay, but they should come back up quickly. So that's why we had to invest in our own job management layer as well. Okay, so that's all I had. So for reference, I mentioned there are 2 papers. These are the names, and you can Google them. You'll learn more about. The second one is about streaming joins, and the first one is more at a high level look at what are the different stream processing services we have at Facebook, and it goes quite into details of Puma, Stylus, and other services. Cool. So that's all I had. Questions? Oh, I think I confused everyone.
Could you show the last link?
Oh, sure.
I was curious if you talk like.
I was curious if you could share a little bit about, you mentioned during lessons learned the global watermarks. Mm-hmm. Currently, we're using things like consumer offsets to manage that. I don't know if Facebook is doing something different, or is there something that can be shared?
So yeah, the global offset, I don't understand the consumer offset thing, but
Kafka consumers.
I see.
So when mirroring.
I see. So right now, in our service, for example, we have the reducer operator. It looks at the input stream, and it maintains a min event time. We call it, minimum event time. 99.99% of the events are about this number. So we use that to track our the window closing time and output time and so on. But I think that is a local view. That's not enough. If some data is stuck in the upstream, maybe in the mapper stage, maybe one of the tasks in the mapper is down, and that's got a lot of events stuck there. And if you don't wait for that, then the output that we're producing will be kind of inaccurate up to a certain. So we encounter that in some of our apps. So for now, we have added the data quality checks to catch, okay, if output that we're producing, is it matching, say, the previous Windows output? Is it off by a certain threshold? Then it's okay. If it is off by more than that, then we say, okay, something is wrong, so we don't publish it. So that's our current solution. But we have another layer that keeps track of the entire DAG and company-wide. So we want to integrate with that and see, before we do any publishing, we want to look at the watermarks of all the other previous nodes and take the minimum of those and then use that for our watermarking. So that's what I mean by global watermarking, and yeah, that's something that we are looking at. Yeah.
Thank you.
Yeah.
Found yourself running into limitations, Kafka or Zuki.
Yeah, we don't use Kafka. We use Scribe for our input. So yeah, we don't.
Sorry, in Scribe itself.
Oh, limitations that affect our.
Like the scale at which you can operate one provisioning unit. I've run into those with Kafka and Zookeeper.
Right.
Run into that with your infrastructure layers. Had to fork them. Had to.
Yeah, I mean, anytime, so Scribe is our main dependency. If anything goes wrong with Scribe, we are impacted badly. So one of the common things we have with them is, sometimes the tailors get stuck talking to the cluster, and that's why we have the auto remediation for that. And I think the other one I would say is there's one more that I don't remember now. But in general, Scribe is very scales really well. So they have the ability to give us this a unified stream irrespective of where you're running, or they can give you a region local streaming. Yeah, okay. The other one that I was thinking was the buckets. So right now we have the buckets which are statically created. So you have like if you create a topic with say 16 buckets. So you're stuck with it, and sometimes we want to increase the, sometimes the lag is so much that we want to clear the lag quickly. We can't do that. So that's why we have asked. That was one of our major asks from them, and they provided us the dynamic bucketing, so which is dynamically, even though initially it started with 16. So now you say I want to repartition that data into say 64. They can do that, and then we can create say 64 tailors to tail that data, and clear the lag quickly. So I would say that is one of the major ones that we were asking for, and which has already come.
What's the most buckets you use in one stream?
I don't know. I'm looking at my colleagues here. I have a few people. Do you know Ben? Yeah, hundreds.
That's the last question. Thank you, Ritin, for
yeah.
Thanks everybody for joining.